Hello and welcome to this BioProcess International Ask the Expert webcast. I'm your host, Leah Rosen, the online editor for BioProcess International. Before we get started, just a couple of notes. The webcast is being recorded and will be made available for replay in the multimedia section of our website. We've muted the audio lines, but we welcome you to type in your questions for our speaker in the chat window on your screen at any time. After the presentation, we will begin the question and answer portion, and I will ask our speaker your questions from the chat window. Your questions in the chat window will only be visible to myself and our speaker. So thank you for joining us today. It is now my pleasure to introduce our speaker, Surendra Balakai from Thermo Fisher Scientific Bioproduction.
Thank you, Leah. So good morning, good afternoon, and good evening, wherever you are in which part of the world. Thank you very much for joining this scientific session and understanding about the bioreactor design and its new concepts of 5-to-1 turn-down ratio and how it helps in terms of intensifying the seed train and scale-up aspects. So many of you from the industry are definitely well knowledgeable about the bioreactor process and design aspects. And in this session, so I'm going to cover some of the critical aspects, especially when we talk about higher turn-down ratio and its impact on the process itself. So we will look at some of the design aspects and then some of the challenges, especially when the turn-down ratio is 5-to-1. That means when you operate the bioreactors at 20% volume, then let's look at some of the challenges from the process point of it as well as the bioreactor design aspects of it. And we will look at some of the examples of the cell culture performance at low volume as well as high volume and look at some conclusions. When we operate the bioreactors at 5-to-1 or 20% volume, some of the primary challenges are the carbon dioxide buildup in the head space due to the metabolic activities. Depending on the cell line, there could be varying amounts of carbon dioxide in the headspace buildup, but it will have a significant impact on the whole cell culture process because it's going to react with your culture and then create an acidic environment, and that acidic environment can have a severe effect on the growth of cells as well as on the viability of the cells. So that is on the process part of it, but otherwise when you look at the dynamics within the whole system, for the 20% volume, the impeller size in the bioreactor could be little, it look like oversized, and the position of the impeller and then the fluid movement within the bioreactor, especially when the volume is low, and then the shear zone. So these are some of the physical aspects that are important to understand. On the other side, the Spargers. So basically, whether you are using a ring Sparger, frit Sparger, or drilled hole Sparger, so it's important to understand the impact of the Sparger and the temperature control aspect. So when the volume goes down, it becomes essential that the vessel is bottom jacketed and it is able to provide an effective heat transfer even at the lower volumes. And since the volumes will be lower, it's also important to make sure that the probes are well immersed into the process liquid and you are able to measure the desired parameters like pH, dissolved oxygen, temperature, and things like that. And of course, what is important when we talk about the single-use bioreactor is the film aspect, the choice of the film itself, and then the surface area to volume ratio, leachable extractables, whether you have a co-extruded film in your process or you have, films with some adhesives in between, those are some of the things that will play an important role in the whole cell culture process. Now, what we have understood from the scientific experiments as well as a large number of studies is that when the volume is lower and when the carbon dioxide buildup on the headspace creates a lot of problems. And in order to avoid that, if you have an overlay on the top, that may not be enough. So let me show you a diagram here. So when you look at this diagram, so typically the overlay is on the top here. And when you provide the overlay from the top, it will not be able to flush out all the gases in the headspace that is built up. And that's the reason we came up with a new type of sparging technology. It's called cross-flow sparging. So here, the gas is introduced at probably the surface level or a little above the surface level of the liquid. So this is to make sure that the metabolic gases, including the carbon dioxide, are flushed out of the bioreactor. So this is a patented technology for Thermo Fisher, and in all the 521 bioreactors that we have released to the market, so we are going to implement this technology. Now let's look at some of the other aspects. So when the volumes are lower, it is important to make sure that the impeller is not hindering with any other type of spargers within the system, and hence it is probably better in a single-use bioreactors to use a drilled hole sparger type of technology, because this is basically a film where you have a laser drilled holes, the precise number of holes and the precise pore size on the film. So that is the type of film that is used as a drilled hole sparger, and there is a uniform bubble size from all these pores. So it provides a very effective carbon dioxide stripping from the culture, as well as it helps in higher flow rate of the gases to push out the gases out of the bioreactor system. Depending on the size of the bioreactor, the number of pores on the drilled hole sparger may vary. So the sizes of the hole itself will increase, as well as the number of holes will increase, to make sure that the bubble sizes are enough and they're able to travel the path of the whole cell culture column of the liquid within the bioreactor and provide enough oxygenation to the cells while stripping the carbon dioxide from the process. So in order to achieve a better performance, so there were certain modifications to the design that were done. So I'll take you through a couple of examples. So one is about the motor angle. This is to make sure that the impeller is not hitting the wall of the bioreactor, but at the same time is able to provide an uniform mixer around the impeller without much significant shear stress or the turbulence like foaming. So cross-flow sparger, as I mentioned, is very critical. So it will be somewhere around this height. So I'll talk about what should be the optimum height for effective cross-flow sparging. And as I mentioned earlier, the probe's positioning is again critical. So when the volume is about 20% of the bioreactor, the probes have to be well immersed into the cell culture fluid. So when we have to have impeller well immersed at 20% of the bioreactor volume, it is important to make sure the length of the shaft is sufficient. At the same time, the shaft is not under any mechanical stresses due to the length of the shaft. And the drilled hole sparger, as I mentioned earlier, is type of a film welded at the bottom of the bioreactor itself, and hence it doesn't pose any extra extensions into the bioreactor. and it is right here at the bottom of the bioreactor itself. With that being some of the design aspects, critical design aspects, so we have looked at the mass transfer efficiency as well as the coefficients for oxygen transfer to the cells, as well as stripping of carbon dioxide from the culture as well as from the headspace. So we have used a standard dynamic methods for measuring the KLAs. As you can see in the graph, use initially the nitrogen to strip off all the oxygen from the system, and then start providing the oxygen, and then it goes up to from 0 to 100%, and then you bring it back, and then you change the parameters, and then again you do that. So we have looked at both oxygen delivery to the cells as well as carbon dioxide stripping, and all this information data is available. Now, one important aspect that I was talking to you about is if you just use the overlay from the top, it is not enough to flush out, but at the same time, it should be an optimum height from the surface of the liquid to flush out the gases. So as you can see from this graph, we have looked at the KLAs of the carbon dioxide stripping against the position of the cross-flow Sparger from the surface. As you can see here, 5, 10, or up to 12 inches from the surface of the liquid. As you go on increasing the flow rates, say 10 liter, 20, 35, or 50 liters per minute, it's very effective in stripping the carbon dioxide. But the moment you increase beyond that, then it goes the efficiency goes down. So that's why it is important that the cross flow position is within the 10 to 12 inches from the liquid surface. So this is a graph to explain about the oxygen transfer KLA values. We saw in the previous example the carbon dioxide stripping. So this is for oxygen transfer. When there is no Sparger, there is no overlay. So this is the KLA, which is less than 2 or 3. And when you use overlay, so probably it's between 4 to 5 or 6. And then when you use the cross-flow sparging, it's from 4 to 8 or so. That's what. So this is another graph explaining probably at about, this is for a 250 liter at 14 liters per minute, and then what is the KLA values for carbon dioxide stripping. So this is for 8 to 10 liters per minute flow rates. So these are all the different the graphs. When the cell culture studies were performed, GIBCO freedom show media was used, the dynamics in an AZT form, as well as efficient feed C plus supplements with 2x concentration. And some of the process parameters that were used was about 20 watts per meter cube per hour agitation, and oxygen as a primary, and then carbon dioxide or nitrogen as needed, and cross-flow sparging at 8 to 10 liters per meter square per minute, and staining ratio of 20%, and then pH of 7.2, and some of the other process parameters listed here. So what is critical for you to observe here is, so these are the graphs when the bioreactors are run at a full volume. So that means at 100% volume. So 50, 100, 250, or 500 liter, all of them pretty much behave in the same way because of the geometry of the bioreactors, as well as the viability part of it. And when you look at this graph, which is most important in this session, is so you have the viability cell graphs against the time at full volume as well as at 20% volume. So that means when you run at 20%, the bioreactor behaves as much as 100% culture. So there is no difference in the performance between a 20%, as you can see these dotted line graphs, to a solid line, which are the 100% process runs. In the same way, when you look at the viability also, there is no any compromise on the viability of the cells. So in this graph, it is to explain that when the volume is reduced, so we try to reduce the speed to make sure that the tip speed and the scalar parameters are similar, and the power input to the liquid is similar. And when we try to decrease the speed, basically the biomass, in fact, was performing a little better. So that shows that the bioreactor design complies to the cell culture requirement or the process requirement aspects of it. The significant benefit that you as a customer would gain is you can go from a 750 milliliter flask directly to a 50-liter bioreactor at 5:1 volume. That means, at 10 liters, you start with 10-liter culture in a 50-liter bioreactor, and then use about 750 ml flask as a seeding. And from there, you can increase the volume to 50 liters. And then after that, you can take that 50 liter into a 2,000-liter bioreactor at 5:1 volume. That means at about 400 liters. And then you can increase the volume to 2,000 liters. So if you see here, you can effectively go from 750 ml flask to a 50-liter bioreactor directly to a 2,000 liter. So you don't need any other sizes in between. And if you are able to do any kind of a perfusion for the seeding at 50-liter scale, then probably you'll be able to use that 50 liter to seed 4 times 2,000-liter bioreactors. So those are some of the cell culture strategies that is explained here, which basically helps in reducing the number of equipment that is required. As you can see in this picture, so there are multiple number of bioreactors used for seeding to come up to the 2,000-liter scale. Well, with this 5:1 version, so you'll be able to go from 50 liters straight away to 2,000-liter scale. So there are fewer equipments, significant reduction of the floor space, as well as the fewer number of connections, fewer number of transfers. That's basically the significant value of this high turn-down ratio bioreactor designs. So in summary, it is not just important that in any bioreactor, if you just reduce the volume, you will be able to operate at 20% or a higher turn-down ratio. It is also important to understand the culture performance, and accordingly, this cross-flow sparging, and then some of the other aspects becomes temperature transfer. Those becomes very important aspects in running the bioreactors at lower volume. So Thermo Fisher being the first one in the market to introduce the stirred-tank bioreactor. Again, when we wanted to look at this particular technology at 5:1, so we had to come up with innovative ideas to meet the process needs so that your cell culture performance is always better. So some of the retrofit kits are available to the bioreactor. Build hole Sparger is an efficient sparging technology. Cross-flow sparging is critical. Scalability is critical, and some of these aspects has been considered into the whole process design. So that's how you can effectively utilize high turn ratio of the bioreactor scale up of the process. So those are some of the slides that I wanted to share.
So Surinder, I'm not sure if it's your headset, but if you're on a headset, it might be easier if you could switch to just a regular handheld phone, because there's a lot of static coming through right now.
So I'm on a headset, in fact.
Oh, well, you sound a lot clearer at the moment, so we'll go with that. Okay. So we've got some questions. The first question is, any issues when cross-flow Sparger is submerged as process volume is increased?
Yes. So the cross-flow Sparger is effective only at the smaller volumes. When the volume is increased, so this has to be, cross-flow Sparger has to be moved up to the overlay because, it cannot function. When the volume is higher, the cross-flow Sparge will not be effective. It is effective only at the small-scale volumes.
Okay. And will Will a customer be able to upgrade a 2-year-old high-performa 2-to-1 bioreactor to a 5-to-1 system?
Yes. So if the bioreactors are high performer design in the last 2 years, they will be able to upgrade with a kit, a 5-to-1 kit, to the 5-to-1 performance.
Okay. And when will the 5-to-1 be available in a 2,000-liter bioreactor?
So this is something we are working on certain qualifications and validation aspects. So we are looking at sometime around mid of next year to be launched to the market.
Okay. And is there an advantage of running 5-to-1 when you want to use it in continuous bioprocessing?
It will definitely give a benefit of the scale-up. So whether you use it on for a continuous processing or for a regular fed batch processes, you'll be able to save the significant number of seed bioreactors as well as the floor space. And of course, in terms of performance, whether it's a fed batch process or continuous processing, the bioreactors will perform the same way.
And can I use the same BPC in 2-to-1 as 5-to-1 bioreactors?
So as I mentioned earlier, there are a couple of design changes, like the extension of the shaft. So accordingly, the sleeve length in the bioreactor will change, and the positioning of the cross-flow Sparger will be another change. So the BPC can be modified to accommodate these new changes, and then the bags can be used. Exactly same bag cannot be used, but a bag can be modified to use in a 5-to-1 bioreactor.
Okay. And is the liquid level overlay pinched off upon scale up, and if so, how? A pinch, clamp, seal?
So one can either use a pinch clamp to seal off the cross-flow Sparger, or they can just disconnect the air line and connect it to the top, or they could use an automatic pinch valves to do the same. So any of these are possible.
Okay. Well, thank you very much, Surendra, and thank you to our audience for joining us. The recorded version of this webcast will be available for on-demand viewing on our website, and as a registered attendee, you'll receive a follow-up email providing you with a direct link. We look forward to having you join us at our future BioProcess International Ask the Expert webcasts. We have a full lineup covering many aspects of bioprocessing scheduled for the duration of the year. Look for those announcements in your inbox. Thank you, Surendra.
Thank you, everyone. Thank you.
Okay. Goodbye.